Welcome everyone to this new lecture about complex numbers. Here we are going to look into the polar representation of any complex number. First, we should learn the two-dimensional coordinate system used to represent complex numbers. As you would correctly guess, a real number line is not enough anymore because we added an imaginary component. Therefore, we need a second dimension to represent the added component. We end up with a two-dimensional coordinate system called the complex plane or Argand diagram. This coordinate system is nothing but the Cartesian plane that we all know and call xy plane. The only difference is that the x-axis now is called the real axis, and the y-axis is now called the imaginary axis. Other than that, nothing really changed. To illustrate how a complex number is located on the plane, let us have an example. 6 plus j2 has a real part of positive 6 and imaginary part of positive 2. Therefore, from origin, we go 6 units to the right and 2 units upwards. And here is the point representing 6 plus j2. Let's have another example. Minus 4 minus j3 has a real part of minus 4, so we go 4 units to the left. And imaginary part of minus 3, so we go through units downwards. And done. Simple, right? Check out 4 more examples. Note that up to this point, all numbers are represented as a real part plus j imaginary part, which is what we call rectangular or Cartesian form. One more thing. It is common to divide the complex plane into 4 quadrants based on the signs of the real and imaginary parts. A positive real and imaginary belongs to the first quarter. A negative real but positive imaginary means that we are in the second quarter. A negative real and imaginary means that we are in the third quarter. And the positive real negative imaginary means we are in the fourth quarter. As we know from vector analysis, any point in Cartesian coordinate system can also be represented by polar form. This should apply for complex plane as well, which gives us another representation of complex numbers. So, if a plus jb is my complex number in rectangular form, then the polar form of this number will be r, which is the length of this vector from 0 plus j0 to a plus jb, and theta, which is the angle it makes with the positive real axis, assuming counterclockwise rotation. In writing, a plus jb is equal to r at the phase of theta, where a is the real part, b is the imaginary part, r is called the modulus or the magnitude or absolute value, theta is called the argument or angle or phase. Let us have some basic examples. We have the numbers 1, j, minus 1, and minus j, and we want to plot them on the complex plane and find their polar representation. Let's start with 1. It is actually 1 plus j0, so the real part is 1 and imaginary part is 0. This point here. Its distance from the origin is 1, and the angle it makes with the real positive axis is 0. So 1 in polar form is 1 at the phase of 0. Now let us see the number j. It is actually 0 plus j1, which puts it up here. Its distance from the origin is still 1, but the angle it makes with the positive real axis is now 90 degrees. So j in polar form is equal to 1 at the phase of 90 degrees. It should be clearer now. Minus 1 equals minus 1 plus j0, which is this point here. Its distance from the origin is still 1, and the angle it makes with the positive real axis is 180 degrees. So minus 1 in polar form is 1 at the phase of 180 degrees. Now to the last one here. Minus j equals 0 minus j1, which is this point. The magnitude is 1, and the phase it makes with the positive real axis counterclockwise is 270 degrees. So minus j in polar form is 1 at the phase of 270 degrees. Notice that there is another way to look into the angle, which is clockwise direction. The angle from the positive real axis clockwise is 90 degrees, which allows us to write the polar form as 1 at the phase of minus 90 degrees, where the negative sign is due to the direction being clockwise opposite to the convention. Worth to notice that 270 degrees and minus 90 degrees are 360 degrees apart, which makes them equivalent in trigonometry. Now let's get into more complicated examples. 1 plus j has a real part of 1 and imaginary part of 1. Its distance from the origin can be found using Pythagoras' theorem as the square root of 1 squared plus 1 squared, which is the square root of 2. And the angle it makes with the positive real axis can be found as the inverse tangent of 1 divided by 1, which equals to 45 degrees. Just simple trigonometry. So 1 plus j in polar form is square root of 2 at the phase of 45 degrees. Let's see 1 minus j. The distance to origin should remain the same, square root of 2. But the angle now is 45 degrees in the clockwise direction, so 1 minus j in polar form is square root of 2 at the phase of minus 45 degrees. Or, if you wish, square root of 2 at the phase of 315 degrees, which is the angle that makes with the positive real axis at counterclockwise direction. Note again that 315 degrees and minus 45 degrees are 360 degrees apart. And here I put the example of minus 1 plus j and minus 1 minus j for completeness. In general, we can transform from the rectangular form to the polar form by determining the magnitude and phase from real and imaginary components. By using Pythagoras' theorem, the magnitude should be equal to the real part squared plus imaginary part squared, all under the square root of 2. And by using trigonometry, the phase should be equal to the inverse tangent of the imaginary part divided by the real part. In writing, if a plus jb is the complex number in rectangular form, then r is equal to the square root of a squared plus b squared, and theta is equal to the tan inverse of b divided by a. Needless to say that the inverse tangent always gives you two solutions that are 180 degrees apart. You should select the correct angle from these solutions based on the quarter that is indicated from the size of real and imaginary parts. This should be clearer with examples. Please check part 2 of this lecture.